Back again. This is going to be part number 9 of Virtual Topologies in MPI and episode number 37 of Learning by Doing MPI. We're going to continue from where we left off. We talked about the first example of MPI neighbor all-to-all V, the vector version of all-to-all. And now we want to see the second example. So let's go with MPI neighbor all-to-all V version 1 example. Again, we are using 8 processes. We have this ring topology, and we are using MPI disk graph adjacent version. And again, in this case, we have that sort of slightly more complex example with variably sized sand buffer. And then in this case, we fill up that with based on the rank of every process. Rank +1 because process 0 is not going to end up with 0. And then we fill up that send buffer with the rank. Send counts is going to be 2, rank +1, rank +1. This is a variable receive count again. And send displacements is going to be 0 and 0. So no displacements, same data being sent. And for receive count, we're going to have source 0, process before +1, source 1 +1, that's process after +1, variable receive count. Receive displacements is going to be 0 and receive count. And so receive buffer is going to be, again, the summation of the sizes of the data that we send from process before and process after. That's going to be source 0 +1, source 1 +1. And the receive buffer, we initialize it with -1 for every sort of elements in that buffer. And we are using MPI neighbor all-to-all V, and we pass in all those proper information. And then you see that print statement uses a for loop because it depends on the receive count, and it's not going to be the same for every sort of process. So we use MPI CC, MPI neighbor, all-to-all V and V1. And then we run it with 8 processes, and then you see the same pattern again here. We have 8 7s being sent and 2 1s being received, 8 7s being received from process 7 and 2 1s being received from process 1. This is the same pattern that we have seen in previous examples as well. So we try to replicate the same example, you see, simplicity and also repetitive patterns to make you basically understand these examples deeply. So nothing very crazy, but the vector version basically gives you flexibility in terms of you have displacements for send and receive. And the only flexibility which is left alone is the number of the different sort of types, or having the option or availability of using an array for types. And this is the last thing that we have here. Again, I forgot to mention that we have MPI neighbor all-to-all W. So I forgot to mention this, MPI neighbor all-to-all W.C and MPI neighbor all-to-all WV1.C, and I forgot to mention here a C. So I forgot to do that, sorry. So here the only difference is that for send types, we have an array. Everything else is the same as before. And what is also interesting here that the displacements, another source of difference is that the displacements are this time in bytes. So we are not basically counting on number of data with a certain type, let's say 5 integers, 2 integers, 1 integer, but this time we're using bytes. So let's jump back into the first example. Everything else is also more or less the same, that it supports sort of this Cartesian communicator, the graph communicators, and also the distributed graph communicators. And then if the communicator is a distributed graph communicator, it is as if this and that. And then we have this template again so that you understand it better. Then the in place option is not meaningful, and then all arguments are significant. And everything basically is repeating itself. So the first example is basically the same topology, the ring topology, same mechanic and everything. We are using this distributed graph with adjacent constructor. And then here's the difference, that the neighborhood collective communication is happening. The send buffer is rank and rank squared. It's the same, exactly the same. But this time around, the displacements are not of type integer. The displacements are of type MPI int, and you can also see it in the standard itself. It says that the send displacements should have this type of MPI int. I'm sorry. And then the receive displacements also need to have this MPI int type. And the reason for that is we are working with number of bytes this time. We're not working with how many of that specific data type. Then everything everything else is the same. And the type, you see that the send types is sort of an array with two arguments or two elements, and both of them are going to be integers because we want to keep the examples exactly similar to each other. So we are sending sort of one integer to every neighboring process. One is going to be the rank, and the other one is going to be rank squared. And yeah, for displacements, we are using this size of int, and the reason for that is, again, we are working with sort of number of bytes, not the number of, how many number of a specific type, one integer, two integer, or whatever. And that's these are the only sources of differences. And then we are using the W, all to all W variation, which gives you full flexibility, and then every process is going to print. So this is essentially the same as all to all V example, but this time it works with bytes. You see everything else is the same. Process 0 again gets 49 and 1. Why? Please go back in the previous episode and understand the reason why. It gets 49 first. So then the second example was, again, similar. So we can go with a higher speed now because everything else is the same. So we have 8 processes again. The ring topology is being used here. But in this case, in this case, again, we have this, rank and rank squared, and then we have our send displacements and send counts, and then we have our send types. It's going to be integers. Then we have receive buffer. Yeah, everything else is the same. So yeah, let's try to run this one. Oh, I'm sorry. This is, oh my lord. It should be V1. We just took a look at the previous example again. So this is the same. We're using the ring topology again. I was just thinking about what's the difference between this example and the previous one. That was the wrong file to open. So we are using this or distributed graph adjacent, but this time again we are making the things a little bit more complicated by using a variably sized send buffer based on the rank of each process, and then we are using this send displacements, receive displacements. We are basically filling up the send buffer with the rank of every process. Same mechanics, everything is the same. The differences are coming from the fact that the displacements should be in terms of bytes. That is why we always have this size of integers. And then we are initializing the receive buffer with -1. And we use this all to all W with proper stuff here, and we try to run this. So MPI CC, MPI neighbor all to all, W, and then V1. And then we run it with 8 processes, and then you see that again we get 8 7s and 2 1s, which are the neighbors of process 7. So as I said, we can speed up a little bit because all of these examples are sort of so simple and they're repetitive. They have the same pattern so that you can see the differences clearly. And each time you can pause the video and take a look at the code, and yeah, you're going to understand everything. And then from here, we're going to go blazingly fast because we are working with non-blocking neighborhood collective communications, which are the same sort of functions, but in non-blocking. And you kind of understand that the non-blocking starts with I for immediate and incomplete. So all of these information, so I have this non-blocking. So all those sort of examples are going to repeat themselves here. For example, we have I neighbor all gather. So I'm not going to go through the text again because everything is the same. I'm just going to show you the code because you're going to see that no magic is happening behind the scenes. And I forgot also to mention that what kind of codes do we have here. MPI iNeighbor all gather, MPI iNeighbor all gather. I have all gather v1 and all gather v2. So sorry, I need to type these things. So CMPI iNeighbor gather .c. Can I copy that to make it faster, please? Hopefully, yes, yes. So this one is going to be v1 and this one is going to be v2. I'm going to take that off and put this one here. I'm sorry for the inconvenience. So I'm just going to show you the code. I'm going to go slowly so that you can pause the video. I'm not going to even comment because everything is the exactly equivalent to what we had in blocking communications. I'm just going to scroll down and try to run every code. Try to compile it and then try to run it. Results even look the same. V1. So this is the example, the version 1 of non-blocking all gather. So you can pause the video, take a look at the code and understand it, but essentially everything is the same. It needs 12 processes. Yeah. But maybe one thing I want to comment is that the difference, of course, comes from the fact that here you're going to have a request handle. The reason for that is since this call is immediate and incomplete, then you always need to have a request handle to check with MPI wait and MPI test to see whether that sort of communication is being done or not. So here probably you can say do something useful. I can also save this. So you run your communication, you can do something useful in between, and then you need to make sure before printing anything, you need to make sure that the communication is being done completely. So the last one on the line was iNeighbor, all gather, and v2. So I'm going to slowly sort of scroll down. You can pause the video and check the code and understand everything. But this is the example, the replication of example 8.2. But in this case, we are using the non-blocking version, MPI CC, MPI iNeighbor all gather v2. And I run it with 4 processes, of course. And this is what we get. Again, since we get -1, if you don't want to get that one, the solution was to use in-degree, if you remember. If you don't remember, please go back to other previous episodes to understand that. So then we had, I'm sorry, I missed this all gather v. So all gather v. So I need to mention this, sorry, MPI iNeighbor all gather v dot cn MPI and MPI iNeighbor all gather v1.c. Gonna put that there. .c. So I'm gonna scroll down quite slowly. This is again the ring topology. Yep. MPI-CC, all gather v.c, and then we run it with 8 processes. This is what we get. MPI iNeighbor all gather v1. I'm going to scroll down slowly so that you can pause the video, check the code, understand everything. Now we try to run it. And take a look at that with 8 processes. Again, the same results, 8 sevens, 2 ones. Now we go to the next one, which is the all-to-all operations, but with non-blocking variations. So I have iNeighbor, all-to-all. What versions do I have? C, MPI, iNeighbor, all-to-all, .c, and MPI. Can I copy? Let's copy and paste this. And this should be V1, and this should be V2. So this is .c. I'm going to scroll down easily. Sorry, not easily, slowly. Of course, easily as well. So this is the ring topology. Again, we do MPI CC, MPI iNeighbor, all-to-all.c. I'm going to run it with 8 processes. Again, you get 49 and 1. You already know what's why is that the case. All-to-all V1 is a Cartesian grid. I'm going to slowly go down, and then MPI CC, iNeighbor, all-to-all V1, and then we run it. Of course, we need 12 processes here, and this is what we get. Again, for process 0, it's going to be 64, this pattern. And then the last one on the line, which was V2, is that 8.2 example. I'm going to go slowly, but this is the non-blocking version of that neighborhood collective communication. V2. We need 4 processes for that. This is what we get. Again, if you don't want to see this -1 in initialization of the receive buffer, you can use in-degree for the size of the receive buffer. The next one on the line is, of course, the V version. Again, I forgot to add that in the text. So all-to-all V, I have only CMPI iNeighbor all-to-all V.c and MPI iNeighbor all-to-all V1.c. So these are the examples. All-to-all V.c. This is the first example. It's that ring topology. Yep. All-to-all V.c, and we run it. I think it was 8 processes, right? Yeah. This is again 49 and 1. And whoops, MPI. And then the V1 version, we go kind of slowly with the ring topology. But this time was the slightly, complex one, variably sized stuff. And V1, we compile it and we run it with 8 processes. Again, we get 8 sevens and 2 ones for process 0. Next one on the line is, of course, the W version, which again, I forgot to put here MPI iNeighbor all-to-all W.c and MPI iNeighbor all-to-all W V1.c. I'm going to save that, and iNeighbor all-to-all W.c. This is again 8 processes, ring topology. Yeah, you can pause the video and check the code. iNeighbor all-to-all W.c, and we run it with 8 processes. 49 and 1 for process 0 again. All-to-all W and V1. Same thing, ring topology, but with variably sized send buffer, slightly more complex. So this is the code. iNeighbor all-to-all W V1, and we run it. Again, same thing, 8 sevens, 2 ones. And the same scenario. I'm just going to show you the code. This is for persistent neighborhood collective communication, but we're going to have the same sort of story here. I can show you pretty quickly the code only. So the first one on the line is MPI neighbor all gather in it. Oops. So the difference here is that here 4 phases are separate. The starting, the initialization, starting, completion, and then waiting and freeing are going to be different. So freeing, so now you have to free your request yourself. Starting needs to do this starting process, and initialization works with this MPI neighbor all gather in it. If you don't know what these things are, please go back and watch the chapter about persistent communication. I think it was in the end of, it should be in the final episodes of point-to-point communication, where we talked about persistent communication, because the next chapter was about partition communication. But this is the only difference. And you can pause the code and take a look at it. So I'm going to basically do this. Whoops. MPI run with A processes. Again, the same story goes here, but I'm going to basically copy this thing because I forgot to add these things here. So C, that thing, and that thing, and that thing, but this is going to have a V1 and this is going to have a V2. Again, the same story goes here. We start with basically the distributed graph. I'm sorry. So we should go with V1 all. So, and then we move on to Cartesian grid. The same drill as before, but this one is with persistent communication pattern. Again, initialization call, starting call, and then you need to wait and make sure before printing anything. And then you need to take care of freeing yourself. All gather init V1. And then I'm going to run it with 12 processes, of course. And this is what we get. And for the last one is all gather init V2. So after the Cartesian one, we go to the example 8.2 again. So I'm going to scroll down slowly. The only difference is that we are using this, I'm sorry, the persistent one. MPI oops, neighbor all gather init V2, and we run it with not 12 processes, but 4. Again, if you don't feel okay with these -1s, go for the solution with in degree to size the receive buffer. Then the next one is the vector version of that. So for some reason, I did put this one here, but I forgot all the ones in between. I don't know. That's very strange to me. So that is all gather V, I suppose, init.c. So this is the ring topology again. I go slowly. You can pause the video, check the code, but everything basically looks the same. All gather V init. Whoops. .c, of course. Then you run it, not with 4 processes, but with 8. And this is what you get. Again, 7 and 1 for process 0. Whoops. Okay, since the rest of this stuff is blazingly fast, I'm going to continue throughout the end of... So this is going to be the last episode. It's probably going to be longer than 25 minutes. But since it's going to be like dubious if I make a separate episode, because everything is... I'm just going to show you the code. It's going to be quite fast. So next one was all gather V init and V1. Oops. So I'm going to slowly go down. You can check the code. And then we're going to run this. v init v1, and then we run it with 8 processes. We get the same again, 8 sevens and 2 1s. Now we go to the next one, which is the all to all, but again, I forgot. Kind of, it's very strange to me. So MPI, it's neighbor all to all. Init.c, that's the first example. I'm gonna slowly go down. It's the ring topology again. So MPI-CC, neighbor all to all, init.c, and we run it with a process. Let's take a look at what sort of variations do we have. We have all to all. Okay, so I'm going to copy this. So see that and that and that, but this should be v2, the version 2 of it. This should be v1. I'm gonna put this one up here. So now let's go to v1. So this is the Cartesian one. Again, with that perfect molecule with 6 sort of neighbors. MPI neighbor all to all init v1. Then we, now I don't make that mistake because this one needs to be run with 12 processes. Now it works. And then the last one on the line, which was, let me use like this, v2. We have to watch it first and then we need to go there. So instead of that, we go with Vim. So this is that example 8.2. You can pause the video and check everything. No magic is happening, but this time we are using persistent communication. I already used this MPI-CC up here. I just need to use MPI run, but not with 12 processes, but with 4 processes. And again, if you don't feel okay with these -1s, you can go use the solution with properly sizing the receive buffer. And then the next one on the line is the V sort of variation, all to all V init.c. This is the first version, 8 processes, ring topology. Again, initialization, starting, completion, separate phases, and then freeing. That's the whole sort of idea behind persistent communication with 8 processes, of course. Yeah. So I'm going to copy that and put this one here. See this and this. I think we have only version 1 here. So this is going to be v1. Well, I compiled it, but I should first show it to you guys. Again, 8 processes, ring topology. Yeah, that slightly complex example with variably size and buffer, based on the rank of every process. Oh, I already compiled it. I just need to run it with 8 processes. Oh, it seems that there's a mistake somewhere. Okay, we're gonna take a look at this one. This sounds not right. Process 7. For process 0, it works okay because we have 8 sevens and 2 1s, but for some reason, process 7 is printing garbage. So let's continue, but we're gonna come back to this one later. So this was v1. So one of the problems that if you copy and paste this stuff, is always you're gonna struggle in the end. Next one is all to all W. W init.c. So I slowly am going to go down. Then I'm going to compile this. And then I'm going to run it with a process. So this seems to work perfectly fine. I need to add C. I'm going to copy and paste that. This is the W version. And most probably we have also a V1 of that. So most probably if the V version, the vector version is problematic, then this version should also be problematic. V1. So I'm going to show you the code first. We're going to go down like that. Everything is the same, but we're working with persistent communication patterns. Okay, this one also works perfectly fine. So for some reason, only the vector version basically printed garbage to us. I want to try it again. It was the all-to-all V in it. V1, I think was this one. Oh no, this one also works fine. So whatever it was, oh, I think it was only happening because the processes were printing. Yeah, this is a print problem. So the processes are mixing up in printing. So there is no order in printing. Yeah, there's no guarantee that every process. So this is MPeach actually being nice that every process basically prints everything in order. But if you want to print everything like in order exactly, then you need to basically find other sort of forcing mechanisms. Yeah. Okay, but that's it. So there was no issue with that. I thought that there might be also a problem with that. But then in the end of this chapter, so that was the W version, we have seen all those variations. And in the end, there was some examples, and we don't care about them. And I'm just going to show you the end. And this is chapter 9, the next chapter. So this is the finish line for chapter 8, which was the virtual topologies in MPI. Yeah, I hope you learned something from all these videos from this chapter, and I hope to see you in the next one.